So what I will talk about a bit is automotive radar. Uh, yeah, and we'll talk about what happens with radars. I won't go very deep into the technical bits of it, but just to give you an overview of how the things actually, or what can be achieved with radar and where the technology is going. So yeah, this the image that you see is the the new BMW iX3. This car is fitted with 5 radars looking externally. Very interestingly, there's also a radar in the grille of this car, and this has just been launched, yeah, in March of this year. We'll go a bit more into what features and things happen with radars, but before that, let me introduce, so to speak, myself. Uh, yeah. So this is me at the last day of college at DBIT. So I am pretty much, yeah, like just one of you guys, but from 15 years ago. Uh, this is also one of my friends and classmates. So both of these guys are my classmates, Alden and Snaden. Zane was also best man at my wedding. He's also godfather of my child. So yeah, life can go in a lot of directions. Yeah, so maybe the friends you have now end up being very close friends, uh, even family. From the education, yeah, I am with my EXTC degree from 2012 from DBIT is when I passed out. I also have a master's in communication and signal processing from TU Ilmenau here in Germany. Uh, People don't really ask that much about their grade and things like this. Yeah, at some point, it's the experience that counts. It's the learning that counts. One thing is one takeaway for me, at least from college life, would be to focus a bit more on understanding the engineering problems and what you can solve with your engineering degree, not so much just the whole getting through the exam bits of it. Yeah. My work experience has been very largely radar focused. So I was a research scientist at Samir, which is in IIT Bombay. For close to about 4 years, I was working in atmospheric radar at the time. After this, I moved to Germany to pursue my master's. Uh, Once that was done, my first job was a radar systems engineer at Audi. Uh, this is the automotive domain. From there, I moved on to radar algorithm development on the raw data processing at Continental. Continental is a radar supplier. So they supply radars to the automotive industries. And finally, after 5 years at Continental, I moved to BMW, so back into the OEM, so the guys that build the car, and I am currently in a radar expert role. Uh, so now let's dig a bit into how what's actually happening with the radar system. So what do you want to see with the radar? So this is pretty much the field of views that the radars in the cars tend to have. Yeah, so you have a front-looking radar that is a bit in the long range. You have corner radars that you see in gray. You can have rear radars, and you can have radars also for the doors to facilitate things like comfort exit and also emergency, or not emergency, but unauthorized door openings. So in principle, the radar is kind of looking all 360 degrees around the cars when you have in the newer cars and things like this. And what actually are you looking at? Yeah. So the radar in a single snapshot can see the range, it can see velocity, it can see angles, so an azimuth and elevation, so a 3D map. And it also sees RCS. RCS is your radar cross section. The nice thing about this is in a single snapshot, you get a lot of information or a lot of data, which is a lot more than what the camera sees. Yeah, the camera doesn't give you range. So to calculate depth in a camera, you need multiple snapshots. The camera cannot see velocity. For this as well, you need multiple snapshots. The camera can do azimuth and elevation a bit, and for sure the camera maybe is a bit better in recognizing objects. But in the end, yeah, when building an entire system for an automotive for a car, you bring everything together. So the strengths of the radar primarily are that they can really do more measurements in one, so more data for the system, and it's a lot more robust. Yeah, there's no blinding issue with lights. There is no blinding issue with weather. Radar pretty much sees through everything. Uh, yeah. So we go a bit now into the operational principles of radar. Crystal, maybe could you run the first question then? So I just want to get an understanding of what you guys think the radar, the how the radar works. Yeah.
Well, I hope students can respond to the app. Yeah.
Yeah. Perfect. So I want to know, do you think how does an automotive radar work? Does it work on an echolocation principle? So, you send a pulse and you receive a pulse. You send a pulse, so you send a pulse, you measure the time, and then you receive a pulse. Hmm. Are we done? It doesn't have to be long, yeah. It's something very quick. So for the two guys, who are the two guys who thinks it's some magic, yeah?
So should I end the poll?
Yeah, let's end the poll.
All right.
So I'm interested in the two people who think. Can I share that? This is it. Who are the two guys who thinks it's something RF magic? I don't know if you need to then. I maybe Crystal, can you tell me who's the two guys who
Yeah,
put
just
the RF?
checking. Just
Yeah.
checking.
Okay, let's not waste time with this. Yeah. The two guys who thought it was a continuous RF magic thing are actually correct. Yeah. The automotive radar does not actually work like a pulsed radar. There are no pulses happening. The modulation scheme that is used is called FMCW, frequency modulated continuous wave. So what's interesting here is you use a principle of RF, which is a mixing principle that is analog, and the physics principle of what happens to signals when they are shifted and through a mixer in a homodyne system. Yeah, so not a heterodyne system, but where you mix your transmitted signal with your received signal together. So in principle, what's going on is, let me maybe just turn off my video, makes it easier. So what happens here is you are sending out a continuous wave. When you receive your wave back, you will receive it with some delta t. When you pass both of these components through a RF mixer, what you get is, in principle, a beat frequency out. So the FB, the beat frequency. The beat frequency is pretty much the difference frequency somehow. So you will get a difference from between. So the FC and FC would cancel out, and what you get in terms of frequency is something that is proportional to the time the wave has traveled and come back. So Now there are two principles in play here. One is your range principle and one is your Doppler principle. Clear, the range you get from the delta of t, but the wave that goes out also gets Doppler shifted, yeah, based on the movement of the target that it has hit. It gets Doppler shifted and comes back. Now you have a problem that you have some shift due to t in phase, so time phase shift, as well as some shift due to Doppler FD. And now it becomes problematic. So if you keep sending continuous waves, so just a single tone frequency, if you keep sending, you wouldn't be able to distinguish between a shift due to Doppler and a shift due to time. So that's where you use something called the FMCW principle. So what we do is we send a wave that has an increasing frequency or a ramp or a chirp. So you're not sending just one frequency, you send it over a total bandwidth. And you start receiving as well at the same time over a certain bandwidth. And now what you get is a difference in time due to range, let's say. And you will also get a difference in frequency. So not necessary that you will get an exactly what you send back, you will get also a bit of changes. They're very minute, of course, because the Doppler frequency is not that high, but you will see a small difference in changes that will correspond to the Doppler. And this is basically the working principle. Yeah, so it is really using a lot of it's understanding the physics behind what happens to an RF wave when it travels in time and also is Doppler shifted, and then using this principle through an RF mixer to kind of get the signal out and build an FMCW radar. So really, in principle, if you wanted to, and if ma'am allows you all to, if you went into the RF lab and if you had an RF mixer, you feed in from one side, uh, you feed in one transmit signal into the RF mixer. So you need a 3-port mixer, and at the other side you place the antenna, horn antenna. So this is your LO. This is no, not a mixer. Needs to be a circulator. Needs to be a circulator. So 3-port circulator. From one side you send your LO. It can be CW. So CW signal. On the other side you have an antenna, and on the other side you get your receive signal, and you pass then these to a mixer. What you will get out if you put this to a spectrum analyzer, as you move in distance from the radar, you will see something on the spectrum analyzer close to the 0 dB frequency. And this is really the operational principle of the radar. It's not sending pulses and receiving pulses. These kind of radars are pulse radars or pulse Doppler radars. These are what you would see in aircrafts, in military systems. So what you said, airports, what you see in boats. These are pulse Doppler systems. These systems are for looking up to 200 kilometers. And for seeing maybe a bit larger targets. For automotive, we want to see a maximum of maybe up to 300 meters. And in that case, the whole modulation scheme or the whole understanding of the radar is a much different one. Okay, that was the first principle. So going back to what we do at the automotive radars. So there is FMCW modulation. That's the modulation scheme we just spoke about. And the operating frequencies are very high. So we are talking 76 to maybe 81 gigahertz are the kind of frequencies that these operate in. And these make miniaturization of the devices. Yeah, so these devices don't have to be very big. They tend to be extremely small. Just to give you an idea of what this looks like, let me pop my video back on again. Is it working? So this is what an automotive radar looks like. This is a So this is the company I used to work with, Continental, and this is a Conti radar. This is the Generation 6 radar. These would be where you stick the power and the Ethernet and everything. And really the whole RF front end is only, the RF front end and the signal processing is only this much. This is a front radar that can look, oh no, this is a side radar that can go up to 300 meters or so. And it's really this much sitting behind the bumpers in the car. Behind the bumpers or behind the front fascia of the car. So let's go. So we go here. Let's go to the second thing. Then there would be the second question. Yeah, Christopher, if you could please run the second question. So the next question would be, how do you think the radar actually finds its target in azimuth? Yeah. I think I kind of gave off the answer. But let's give 10 seconds more. Yeah. So 4, 3, 2, 1. Let's end the poll. So what you would expect in a radar system, again, going by conventionally, when you think of radars, is you're going to have something rotating, yeah, something that's moving around and looking for targets. So this is what you see in, I don't know, movies and stuff like this. But again, if I show you back my radar, let's go back soon. Let's start the video. Yeah, close. Let's start the video again. So again, this is what the radar looks like. It's just this much. There is no moving parts in it. There was at some very early generation. So in the starting of the 2000s, there was a rotating drum radar that had the antennas rotating. This did not sell very well and it stopped immediately, almost immediately. But there is nothing inside here. So this radar can look plus minus 45 degrees in elevation and plus minus 20 degrees in azimuth. But it does not have any moving parts. So how does this work? Let's go back to the drawing board. I hope you guys have done a bit of antenna arrays. So let's assume we have, again, let's take a 4 antenna array. These terrible drawings of mine are 4 antennas here. And now let's assume we have an incident plane wave on the antenna. So what you get is that when I sample all of these, so I send all of these to an ADC, the signal, because it's coming at an angle, okay, there's an angle theta over here, so an azimuth angle, it reaches transmitter 1, receiver 1, a little bit before it reaches receiver 4. So in principle, if I, let's say, plotted what came out of the ADC, this is now a very rough estimation, yeah. So what we sent out was a continuous wave. So when I receive back, I would expect 4 copies again of the continuous wave. But what I get is I get a FC plus delta t plus delta t plus theta plus delta t plus theta 2 plus theta 3. So I'm going to get from this ADC from every antenna a bit of shifted. The signal is going to be a bit shifted in phase only because the antennas are not are sampling different points in space, so they are receiving data that is a bit shifted in phase. Yeah, again RF magic. So now here's the DSP magic. I receive in each. So this is my sine wave, and I am this is what I receive back, and I'm sampling at each antenna a different phase point because they are not placed at the same place in space. They are placed a bit different in space. So I am sampling the wave in a way that I am not seeing the same part of the wave, but I'm seeing different parts of the wave. And in principle, once you take the data from the antennas and you place them in a series, so you place them one behind the other, and you do an FFT out of it, what you will get is the frequency corresponding a bit to this curve here. So now what you have, this is the principle of beamforming. What you get is an FS, so a spatial frequency. That's the terminology. That is not equal to, but it's proportional to the incident angle or the direction of arrival, theta. And this is the concept in massive MIMO. So even your phones, 5G, 4G onwards, in fact, do have something called beamforming or beam steering. What we do in radar is we do a direction of arrival analysis, so DOA estimation. And what we do in the DOA estimation is we transmit from multiple antennas and receive together as well in multiple antennas. And the antennas are designed in a way, so they are sparse arrays, but in principle, if we go back to Nyquist theory, yeah, to find a frequency, you need to sample at double the fundamental frequency. So if you assume that your fundamental frequency is your carrier frequency, FC, if you are able to sample, so now you go back to lambda, if you are able to sample twice of it, so FC is 1 lambda, you need to sample at least 0.5 lambda, you will get an unaliased beam. And how you do it in practice, so to say, is you let's take a simple radar system. So you have 2 TX that are, I don't know, let's say 2 lambda apart, and you take 4 RX that are lambda over 2 apart. What you will get in principle, what you will get at some point is, since you are sending all at the same time and receiving all at the same time from receiver 1, from the signal from transmitter 1 will be 4 samples in time that are lambda half apart, and last color. So this is lambda half. So this is 1 lambda. This is 2 lambda. And now the signal that comes from transmitter 2 will be again lambda half apart. So in principle, your virtual array is increased in aperture, and you are able to get, so wider aperture of an antenna would mean tighter beams, better beam forming, better angular resolution. And this is exactly how the radar systems that we have are so miniaturized. You work a lot more in using these kind of DSP techniques, RF techniques, you make the antennas really small, really tiny, but manage to get amazing resolution out. So let's go back to the presentation then quickly. Oops. So these are the two points that I wanted to touch on a bit because it's a lot more physical. It's a lot more deeper understanding of physics and a lot more understanding of basic principles. So FMCW modulation and phased array. On top of that, what you need to have is a lot of AI based recognition and stuff. So we do have a lot of algorithms then that are able to recognize objects. So things like finding microdoppler signatures, because when you're looking at a car, for example, the Doppler from the wheels is different from the Doppler of the body. If there's a pedestrian walking, the hands and legs tend to have a different frequency as compared to the whole body moving. Then you do AI-based segmentation and road feature recognition. So you are able to tell where the road boundaries are, you are able to tell where the sign gantries are. All of this somehow you can pull out of the radar data. We'll look into this a bit more. So now what the state of the art really looks like. So for example, we have waveguide antenna. So if you see the little image with the plate, the copper plate, this is what the inside of the antenna looks like. Yeah, they are slotted waveguides. And the chip, so the whole radar, really the whole RF front end plus the first part of the DSP, so the hardware accelerated DSP, so all of your FFTs, so the signal processing magic that can do up to the beamforming is really on a chip that is that small. And that chip is capable of 8 transmitters and 8 receivers, if you would believe it. Yeah, it's really the size of the finger. It'll fit on your finger really, and it has 8 transmitters, 8 receivers at about, if I'm not mistaken, 13 milliwatts each. Each transmitter transmits at 13 milliwatts. No, yeah, close to minus 10 dBm. And the beauty of the new chips, we have something called a launch on package. So from the chips, you can launch directly into a waveguide. Say the signal is generated on the chip and shot straight into the waveguide antenna. And through the antenna, then it goes, and you have these funny antenna patterns that really let you transmit with different virtual arrays. So you adjust your transmitters and receivers in a way that you get virtual arrays that look exciting. Why do they need to look exciting? Because you want to use algorithms. So the other state of the art is, of course, using different algorithms. So it's not yet AI based because this is still very physical. Yeah. So you have something called compressive sensing. Compressive sensing is a technique that beats Nyquist. So you don't need to sample at the Nyquist frequency. You can sample far below the Nyquist frequency. So you don't need to sample at twice the highest frequency that you're looking for. You can sample much, 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 much lower. That means a lot less data that you have to work with. It is based on a lot of principles of sparsity and stuff like this. But this is really the state of the art, doing compressive sensing, direction of arrival. And the next thing is to do AI powered raw data analysis, where you don't process the signal out through CFA processing and things like this, but you really use AI straight on the radar cube or straight on the raw data, and you try to get features out. That's the working state of the art. And then I also want to maybe get you all into what is research happening in this field. So you have to understand this is a field which is quite high RF dominated. It is going more into the direction of software defined radio, so SDRs. And the DSP part is very exciting right now. There is a lot of research in antenna design and making everything miniature. Yeah. So you want to make it as small as you can, but extract as much data as you can. Doing a lot of real-time algos because these algorithms are expensive. They cost a lot of processing power. And the processors that we use on a radar, extremely low. So they're not expected to be, because these are commercial items, they cannot be very expensive. Of course, as more and more cars come onto the market with radars, interference is a problem. How will you do interference suppression? How can you reconstruct the signals after interference? Big, big research area. How do you use AI? Or how do you feed the data into an AI model better? Is another big research area. A lot of the semiconductor industry is also pushing, they want to make these chips more efficient, more power saving, because now with electric cars, you can't have the radar eating a lot of power. So with there's a lot of thought going into how can we use smaller nanometer scale devices. How can we add more MIMO devices into a single chip? How can the chips work better? How can we do faster FFT algorithms, DFT algorithms, all of this inside? There is a big push on how do you validate radar data? Like, how do you know that the point cloud is making sense or not making sense? And how can you do low-level sensor fusion? These are a lot of areas of research. If you start looking into it, if you would like to go into your bachelor thesis or something like this, you can find data sets as well, because I know AI is right now the big trend. For sure, doing AI without basic physical understanding of the radar systems is more like luck. But there are data sets, so you can get data sets with radar raw data along with annotated, so labeled camera or labeled radar data, so to speak. And you can use this data then to either come up with interesting models or come up with feature extractions and things like this. It is easily available, it's all open source, and it's in demand. Just for your information, not a lot of, all of the radar suppliers, except for maybe the ones that are based out of China, have development centers in India. So there are a lot of jobs, not in Mumbai. Of course, all of the centers are in Bangalore. There is maybe a few centers in Pune that have opened, but the market, I believe, is still, if you have the right skill set, the right expertise, there is still a market to work in automotive, in India. None of the applications, I think, really make it to the Indian roads, but a lot of the development is really actually happening in India. So now what I want to go is just show you a bit of what the radar actually sees. So these are just some videos I pulled out of the internet. So I'm going to run them. I hope the videos are playing through. So these are some of the corner radar systems. And really, this is the point cloud of what the radar is seeing. And the colors are a bit of they mark the distance. So the distance to the distance and the velocity to the radar. So in principle, this is how good the radars are. So you can get enough features to recognize pedestrians and even something as small as a ball. So this is one small preview of what the radar sees. And and it's all 3D. You can see the speed of the ball, you can see the height of the pedestrians, everything in a 3D point cloud. So next, I would show you what the radar sees when it's on the road. It's again something I pulled off the internet. So here as well, okay, never mind. So the radars are placed on the four corners of the car. And if I pause the radar here, you can see while this car is driving along the path over here, you can see all the trees are clearly available. You can see how the road boundaries are clearly visible. And you also see the small entrance to the parking lot where the car turns into right now. So you see how well everything is kept and maintained with the radar. Of course, radars are nice, but in the end, you really need sensor fusion, As you start getting into a bit more exciting applications. And Arbe is one of companies that like to do a lot of low-level sensor fusion. So right now, you can see why cameras don't really work all the time. Yeah, darkness, challenging weather, glare doesn't help. But what helps is then taking the camera data, fusing it with the radar data, and building then a whole environment model that the car can understand how and where to drive in. And this is what it looks like, yeah. So I think green is the fuse data, red is camera only, and blue is radar only. So you can see that the radar can see a lot more and a lot wider than what a camera can see. And then you will see what happens when the data starts getting fused. So you take the best of both worlds, so to speak. And that's how the whole system is built. So here you can see in the camera, yeah, almost nothing. You cannot see a pedestrian running through, but the radar doesn't care. Radar can see it, and in the radar data you see it, and in the fuse data you can see extremely clearly, yeah, that the radar has no problem and the fused object has no problem seeing the pedestrian at night. When you go long range, the cameras are never that good. Yeah, they can barely see anything. The radar can see 200-300 meters, no problem. And fuse both together, the car can see a lot better. Camera, of course, has its issues with light. So if it's too bright outside and too dark inside, the camera is blind. Radar doesn't matter. And this is what you see in this example. There's some examples with highway fusion. So the highway driving is a bit dynamic where things are happening very quickly. And then you need the radar to be able to kind of help with these things. So you can see how much of data the radar is generating, and it's quite clear. Yeah. Oops. But yeah, this is pretty much how, when you have a fused system, you can do a free space analysis. You can understand where the car can make movement into. And you can see the radar can track a lot of objects. Yeah, we have currently about 250 objects that we can track on a single with the radar. And it makes it a lot more robust that we are able to do some kind of autonomous driving features and things like this. But yeah, I'll stop this video at this point and then show you something that we do on BMW side. So what now can the radar let us achieve? So this is the new iX3. This was launched around last year and is now commercially available already. In Germany, it's the full electric i3. And what we have on the new i3 is the highway assistant. So 130 kilometers, hands-off driving. And really, it's actually like that, yeah, where if you need to change lane, if you need to change lane, you just need to look to the side. So once the assisted driving is on and you need to do a lane change, you would look out into the window to make sure it's clear. And once the car has recognized that you've cleared it to turn, it can turn and overtake up to 130 kilometers an hour. So I will end the presentation with this and open the floor to any questions from you guys.
Krishna will open the chat. So participants can now put your queries in the chat box.
Hello, sir.
Hi. Who am I talking to though? You'd have to introduce yourself before, yeah?
Yeah, I'm Christopher only, sir.
Okay, sorry.
So before I start, I have really wanted to say this one line. Guten Tag, and I hope you are
Yes,
doing well.
servus, guten Tag.
Uh,
Ja, ich bin gut. Ich hoffe
uh,
dir
s-
auch.
I just learned the starting line actually. Uh, but yeah, one thing about your presentation that immediately caught my attention was I think you said something about compressive sensing, which
Mhm.
bypasses the limitation created by the Nyquist theorem that we need the
Yeah.
sampling frequency to be 2 times the carrier frequency. Could you elaborate more on that?
Okay, so Nyquist theory is that yeah, you have to be twice the greatest frequency. What compressive sensing has its roots in is that signals are inherently sparse. So when you send a sine wave, you pretty much know what you're going to get back. So you can predict where a sine wave is going to travel. Or you can predict the shape, pretty much predict the shape of the sine wave. So if you have a priori knowledge of, for example, what the sine wave looks like. So I know that I'm sending out a chirp with a certain frequency. So starting at a certain frequency, ending at a certain frequency with a linear ramp. I know that I'm expecting back pretty much the same thing. Because I know that, I can make certain assumptions. Uh, it's different, yeah. So, and because I can make certain assumptions, I don't need uniform sampling. So that is also Nyquist states that in a uniform sampling environment. So you need to sample uniformly and twice the highest frequency. In compressive sensing, you sample randomly and not at the Nyquist frequency based on the fact that you have a priori knowledge of what signal you are expecting. And then it boils down to a minimization problem. It is not anymore a pure physics issue of reconstruction, but it's a minimization problem. So now I'm not interested in reconstructing the sine wave, but I am interested in finding the spatial frequency of that sine wave. So once you formulate the problem differently, you don't need to sample at Nyquist. You can go much sub-Nyquist in sampling in a sparse manner. So non-uniform sparse sampling, much below Nyquist, and you will be able to reconstruct the signal as easily as ever. The maths behind it is a bit more complicated. It is more in yeah, we'll have to dive very deep into linear algebra to understand it. But in principle, you convert the problem into a minimization problem. So the same things that the machine learning guys are doing. Yeah, you want to find the least squares error between two of the signals that you have. So your input signal and an output signal, and then you can find the difference. I would suggest to read up on compressive sensing. It is fairly new from a algorithm point of view. If you consider the FFTs are 1950s technology, compressive sensing is something that came into the world, or the idea of compressive sensing came up in 2002, 2003, I think was the paper that first introduced compressive sensing. But you'll have to read up about it. It's not that easy to explain. It's a bit abstract because there is also the consideration of sparsity. Yeah? That if you assume that your signal is very sparse, when I mean sparse, it means there's not that much data. So if I'm sampling, I don't know, 1 million points, maybe 10,000 of those points really have data inside. This is where sparsity works, or this is where compressive sensing works. But yeah, I we would have to do like a 3 lecture series to cover compressive sensing. But in principle, yeah, it is possible. It is a minimization problem, and it is possible.
Thank you, Jason. Thank you, sir. Got it. I was quite curious that there was something that bypasses Nyquist. So that's why I
Oh
asked.
yeah, you can read it up. It's very big in things. It's very big in it bypasses Nyquist, but it requires a lot of processing power. So in places where you want to do reconstruction, but you do not have either you do not have enough of snapshots or you do not want to expose somebody to too many snapshots. For example, if you are doing CT imaging or if you're doing ultrasounds, where you don't want a person being blasted either with sound waves or with CT. So that's accelerated particles and stuff like this. So you want to take one snapshot, but you want to reconstruct and get as much info out of it. This is where you would go into compressive sensing. So you don't have that much data, but you want to extract a lot more data out of it. And the thing is that the processing power is getting much nicer. There's a lot more that is able to solve minimization. This is the whole AI boom. Yeah, AI is in principle minimization in the background. So that's why compressive sensing is we are being able to put this onto much smaller devices now. So onto embedded hardware. Okay, I see one question from Darshan. So in the BMW vehicle, if a driver looks outside by mistake, oh yeah, for sure. So a lot of studies have been done. If you're having a conversation in your car and you're looking here and there while talking to the person, it pretty much ignores it. So there is also a lot of AI-based behavioral things. And there are, I think, 3 cameras looking at you on the inside of the cockpit, one from the front, so from your driver's display, one from the mirror, and one from the other side. It is able to tell. It's not foolproof. Sometimes it does make a mistake, but it only gives you, let's say, the car will ask you. So if you're driving behind so you've set your speed to 130, and you're driving behind someone who is driving a bit slower, yeah. So the car will ask you, "Hey, do you want to overtake?" So it'll send you a bing, yeah, bing. We like to overtake, and it will show you in which directions it can overtake. What you do when you look out the window is you are checking, in principle, checking the mirror to see if the rear is fine. And if you look out, because this is not an L3 system, L3 is a full autonomous, and an L2.5 system where the driver is still supposed to give a bit of permission for the car to make the changes. So when you look outside, what you're doing is you're giving the car permission, and it doesn't happen all the time. So it's not going to lane change unless it has. So it'll ask you first, "Hey, do you want to lane change?" Then you look outside, and then it will lane change. But it's done a lot better. Yeah. So they check for if you are having a conversation, what your behavior is, if you are looking out intentionally, non-intentionally. This is also taken into account in the camera processing that's inside the car. Once again, does it track the eye movement and cross-check? Yes, it does track a bit the eye movement, and it also tracks the head movement a bit. That was from Vaibhav. The next is from Vineet. How do environmental factors affect the radar performance? They don't. With rain, sometimes. So not with rain, but if by chance it happens that water gets into the radar. So this is the radar housing, and there's a bumper in front. If by chance snow or water gets in behind, you might have affected performance at the angle. Performance gets a bit bad. But there are algorithms inside the radar that detect this. Yeah. So the radar sees that, hey, I can't see anymore as good as I used to. And it will tell you that, hey, I think I'm blocked. That's radar blockage. But in principle, fog has zero effect on the radar. The radar can still see as good as it always does. From Frida ma'am. Oh. Can you suggest small projects in the area of DSP and RF for students, considering the lab facilities are basic? So again, from the DSP perspective, I would look at data sets. So there are data sets from New Scenes. New Scenes is, I think, one of the oldest and biggest radar data sets that we've had that I know of. But you can look up for annotated radar data sets, and you will get immediately data. What you do with the data then is up to you. You can do your typical recognition stuff. You can try, if you all have SDRs in the college, you can try building a radar. It's really as simple as that. You send a from the transmitter, you send a FM signal, so linear FM, and you receive the linear FM, and you can pretty much do the whole first chain signal processing as well. Along with strong core engineering concept, what are the skills important for students to succeed in global companies? Communication skills. I think these are your soft skills are maybe far more important than your engineering skills. Yeah, so you can solve a problem is good. You should be able to communicate that you can solve the problem and communicate it well. Maybe one thing, yeah, something I've noticed a lot. Students send a lot of LinkedIn requests. So request on LinkedIn. But you've maybe not formally met the person. And in this case, more often than not, your requests might just get thrown away. Or if someone is, whatever, there are 100 requests, yeah, whatever, someone's just clicking through them. Whenever you send a LinkedIn request, and if you really want a chance to get in touch with somebody, drop in a message. It will improve your chances that somebody reads through and gets back to you. Yeah. So if you may have a question, someone might be more than happy to answer. Or if you are really contacting not recruiters, but let's say hiring managers or technical managers, you can ask questions. It will open a door for you. Don't just send a LinkedIn request. And the thing is, once you've sent the LinkedIn request, if you wait for them to accept and then reply to you, chances are you already missed your opening, yeah, your first door. Whenever you send LinkedIn request, add a note. It goes a long way. Then to Aditya, in a beamforming radar, what antenna architectures stack batch? So it is an array architecture, but and the old school, let's call it, architecture was to have patch antennas that are so parasitic antennas. So they are patch antennas, but parasitic, and they are along the elevation so that you get a fan beam in azimuth. But the newer radar systems are all slot antennas. It's no more patch. Some companies still do patch. They are not very good radars. Right now, the high performance radars are all through waveguide antennas. So waveguide slot antennas. And this also lets you take on the launch on package architecture where you can directly launch your RF signal into your antenna substrate and into the antenna and not have to go from go to a waveguide system and not waveguide, but go to a strip line and change it and whatever. Okay. I'd go to the next question from Vineet. How can a radar be used in a smart traffic controller system? This is interesting. In Germany, we do have the Ampels. Good Lord, it's an Ampel. Traffic lights. The traffic lights that are overhanging, they have radars on them, and they look into the distance. As I said, yeah, the radar can look 300 kilometers, 300 meters. And what you do is the whole traffic network, so the whole signals are interconnected to each other. And the timing of the signal then is used to adjust the traffic. You can put green for longer or red for longer and adjust the traffic flow based on how much of traffic you see in different directions. This has been used a bit in smart traffic control systems. What let's say the end goal of autonomous driving is that all cars have radars. Everyone is autonomous in nature, and what you achieve with that is when a signal goes green, all cars start moving at the same time. It's not like you start moving when the car in front of you starts moving. This is the dream. This is the ultimate cure to traffic jams. But we're far away from this. Maybe 5 years, 6 years from now. Darshan, so will the radar system would be effective in Indian traffic? I think so, yes. The systems would be quite effective in Indian traffic scenarios. There are issues with regulation and pricing, is the reason why these systems don't come really to India, to be honest. But BMW doesn't, but Continental, the company I worked with previously, had test cars, so test vehicles in India, so they would drive around in Bangalore. And we've looked at the radar data. It's not as bad as you would think it is. And when I'm talking, so the systems that we have now on the iX3, these are uh, L2.5 systems. Yeah, so these are systems where the car drives itself. But from a safety system, yes, the radar is extremely important. In fact, my whole goal of joining radar system or joining automotive radar was automotive safety. Yeah. So when I was in college as well for my bachelor thesis, I attempted to make an automotive radar system. Frida ma'am was my supervisor at the time, believe it or not. Uh, I attended something, whatever, it was a college project, but it was the start of a system. And for me, the goal was to have roads safe. India has terrible accident ratios. Yeah. In fact, one of my friends, for the year I joined 2010, 2012 I passed out. In 2010, I lost one of my very close friends to a road accident. And I said, "Ah, it cannot be so bad. Uh, whose fault it is? You never know, yeah? It's a road accident. How can technology help? Radars." And I started researching, and turns out automotive radar was already in series vehicles all over the world, just not in India. So I said, hey, let's make something, whatever. But from a safety perspective, the emergency braking systems that are enabled through these radars are far more safer than the human driver. So in Europe, all cars are mandated to have emergency braking that is radar driven. These are regulations that just don't come to India. I don't know why, but it's extremely safe. So when I'm driving my current car as well, this has a a long range front radar. I can be rest assured if I make a mistake, the car will hit the brakes immediately. Uh, Next question from Amay. How effective can radars be used for static object detection? It's extremely good for static. It's better for moving because you separate also in Doppler, but also for static, it's extremely good. Uh, we have been able to, so one of the scenarios that you need to fulfill is something called lost cargo detection. You are able, you are supposed to be able to find if you are driving on the Autobahn, for example, and for some reason, let's say a tire is on the Autobahn or a piece of tires on the Autobahn, you're supposed to be able to detect it and react to it in time. The radars that I have built and worked on, we can detect these things at 200 meters. So the radar can see there's a tire on the road 200 meters away, driving at 150 kilometers an hour. From Cristobal, can you share your experience about how you pursued further studies in Germany, made a career there, journey after DBIT? So I immediately after DBIT. So maybe one more thing. So I was I am a diploma student. Yeah. So I joined DBIT in the second year. So I joined DBIT in the second year from my diploma in DBIT. Then, yeah, we completed the course. And after the course, I did not want to work in IT. Yeah. So in IT services, for me, it was important that, hey, and I had a lot of fun learning in DBIT. Uh, and the RF world was something new. Yeah. So my diploma was in power electronics, Father Agnes Vashi, industrial electronics. And it moved on then to RF engineering, which again got very exciting. And then I wanted to get into the core industry. I took a job at Samir, saw it in the paper, there was an opening, something radar. Said, okay, let's go, let's figure it out. Maybe one thing that you have to keep in mind as a student is your first, let's say, 4 to 5 years, you don't work for the money, yeah? You work for the experience. If your financial situation allows you to not have to get a job that pays bills, it is just, yeah, your parents are able to support you, everything is okay. Use those initial years to gain experience. And that's what I got in Samir. In Samir, I have worked on amazing systems. Yeah. I've used equipment that is ridiculously expensive. Most big companies will not allow students to go anywhere near these kind of systems. So I worked on the 36 gigahertz cloud profiling radar and a 212 megahertz ST radar at Samir. Amazing systems. Lots of work. So you have to work from the RF front end, doing measurements, measuring antennas, designing antennas, doing a bit of DSP, doing a bit of controlling controller systems, small boards, RF distribution networks, all this kind of work. It wasn't a very flashy job, but it was experience, gained amazing amount of experience. And in Samir, I realized that, hey, DSP, signal processing is very interesting, but I could not understand anything about it. Yeah, it made no sense. I didn't have the kind of training to read papers about DSP. I couldn't make sense of them. Uh, that's when I decided, hey, I need to maybe study further. Why did I choose Germany at the time is mainly because it's a tuition-free experience. So you don't pay for your tuition, you only pay for your boarding, lodging. It comes with the challenge that you have to be able to accept the culture and the language here. You need to get over it. Nobody cares that you speak amazing English because you need to speak German here. But I made the shift. I came to Germany. I did my master's in communication and signal processing. In the meanwhile, during my studies as well, got into the research labs. So a lot of people here start going into odd jobs and things like this because of the money. I was maybe fortunate enough that I didn't have to really I just needed enough money to pay my rent. I didn't care for more than that. Got into the research facilities, built up experience in, again, research. So I worked at the Fraunhofer IIS, at the MMT, so the measurements department at my university, understanding automotive channel modeling, automotive something, trying to get into what automotive radar really is. And from there, I got out of university, got into Audi, and then once you get your first break, everything falls in place, everything falls in line. But yeah, language is important for Germany at least. But really, once you are in, it's a passion project. You understand what things are. It just right place, right time, right place, right time as well. I was fortunate to be in the right place at the right time with things. And that would pretty much be my journey until this point. Are there any further questions?
No, I think we have closed the chat.
Okay.
So that it was very nice of you, Jason, for taking this, time out from your busy schedule. And I know you have a small baby. Yeah. Thank you so much. I will request our Vice Chair of IEEE DBIT MTTS to propose a vote of thanks.
Good afternoon, Jannavi Shezwar, IEEE DBIT.
You're not audible. You're not audible.
Good afternoon, everyone. I, Jannavi Shezwar, IEEE DBIT MTTS Vice Chairperson, would like to express my sincere thanks to our speaker, Jason Fernandez, for such an insightful and engaging online session on radar system. So the session has truly helped us understand the importance of radar system in modern automotive technology. What truly stood out was how these theoretical subjects or concepts are not just limited to textbooks but are actively implemented in real world automotive radar system. I would also like to extend our heartfelt gratitude to our IEEE faculty advisor, Ms. Frida, for her continuous guidance and motivation. I would also like to thank IEEE DBIT Student Branch and IEEE Microwave Theory and Technology Society for organizing this informative webinar. A special thanks to all the coordinators and volunteers for ensuring the smooth conduct of this online session and to all the participants for joining and making it interactive. With this, we conclude our today's session. Thank you everyone and have a great day. Thank you so much, sir.
Thank you, everybody. Bye-bye.
Thank you. Thank you. Bye. Bye.
Everyone, before leaving, there will be a feedback form which will get the link will be shared on the chat. Please fill it.